Prologue. In 1663, Henry Lucas, a Cambridge MP with a bibliophile soul, endowed a new professorship meant to yoke the old arts of geometry and astronomy to the university's future. King Charles II sealed the foundation on the 18th of January 1664. Ever since, the Lucasian Chair of Mathematics has been a running thread through the history of ideas, Newtonian in one century, quantum in another, yet always anchored in Cambridge. The roll of holders reads like a compact history of physics and mathematics, from Isaac Barrow and Isaac Newton through Stephen Hawking to Michael Cates today. Episode 1. Isaac Barrow, 1663 to 1669, the geometer who handed the torch. When the Lucasian chair came into being, Cambridge turned to a scholar whose mind moved as readily among Greek orations as among curves and tangents. Isaac Barrow, born in London in 1630, had already been Regius Professor of Greek. He relinquished that position for the brand-new mathematics chair in 1663, an early sign that the new professorship would privilege discovery over decorum. Barrow's turn from classics to mathematics was decisive for Cambridge. His lectures began drawing a line from Euclid's geometry to the infinitesimal methods still gelling in Europe. Barrow's life carried more color than one expects of a 17th-century don. As a young man, he wandered the intellectual Mediterranean, Paris, Florence, Constantinople, absorbing the work of Roberval and Viviani and haunting the Medici Library. On the way to Turkey, he helped fend off a pirate attack. Stranded at Smyrna, he read, lectured, and waited out his ship. Friends later remembered a small, pale scholar, slovenly in dress and addicted to tobacco, but also brave and witty, the sort of man who could match swords with corsairs and syllogisms with courtiers. This unlikely blend appealed to Charles II, who, when naming Barrow Master of Trinity in 1672, is said to have called him the best scholar in England. In that role, Barrow helped establish the college library that would later house Newton's legacy. The intellectual core of Barrow's Lucasian tenure was a set of lectures that became the Lectiones Opticae, 1669, and Lectiones Geometricae, 1670. In these, he pursued a rigorous geometric approach to what we now call calculus, focusing on tangents, slopes, and quadratures areas. Barrow offered a geometric proof of what would become the fundamental theorem of calculus, the deep reciprocity between differentiation and integration, years before Newton's and Leibniz's analytic notations conquered Europe. Historians have traced close parallels between Barrow's propositions and later presentations by Leibniz. Even amid the famous priority disputes, Barrow's role as a crucial bridge is increasingly recognized. Barrow's most consequential act, however, involved mentorship. Among the students attending his lectures at Trinity was a 20-something Isaac Newton. Barrow encouraged Newton's private investigations and, in 1669, took the extraordinary step of resigning the Lucasian chair specifically in Newton's favor. The gesture was more than academic courtesy. It was a deliberate handing over of an intellectual project, from the geometric schoolman to a new kind of natural philosopher who would synthesize celestial mechanics and terrestrial physics. Barrow then turned to theology and administration, leaving behind a scholarly corpus whose austerity belied its seeds of revolution. The chair he vacated and the library he nurtured would soon become the staging ground for a new mechanics of the universe. Odd facts to keep. Barrow once saved a ship from pirates. He was an inveterate smoker, and he calculated the tangent to the exotic Kappa curve, a tiny sign of his lifelong affection for geometric craftsmanship. These quirks do not diminish his claim as one of calculus's earliest rigorizers. They make him more vividly the man who passed the torch at exactly the right moment. Episode 2. Isaac Newton, 1669 to 1702. The reluctant lecturer who rewrote nature. Newton was only 26 when he succeeded Barrow as Lucasian professor. His appointment entailed an awkward Cambridge custom. Fellows were generally expected to take Anglican holy orders within 7 years. Newton, already sliding toward heterodox views on the Trinity, wanted no part of that. He secured a remarkable royal dispensation, Charles II exempted the Lucasian professor in perpetuity from the ordination requirement. The exemption quietly protected Newton's conscience and his position, an administrative footnote that changed the conditions for high-level science in Britain. Despite the chair's prestige, Newton hardly filled lecture rooms. His assistant, Humphrey Newton, no relation, recorded that when nobody came, the professor would lecture to the walls for 15 minutes, fulfilling duty before rushing back to prisms, mirrors, and manuscripts. For Newton, the Lucasian platform was less a stage than a legal cover under which to pursue an all-encompassing project. He was shy of crowds, but not of truth. From that cover emerged a cascade, the method of fluxions, calculus, a reflecting telescope that cured chromatic aberration, a theory of color grounded in prismatic experiments, and ultimately a universal mechanics. The Principia, 1687, re-wove terrestrial motion and celestial gravitation into one fabric. The Lucasian seat did not cause this synthesis, but it gave Newton an institutional spine, a duty to teach that he transformed into the time and freedom to think. In the chair's orbit, Newton trained and sometimes tormented students such as Roger Coates, who later edited the second edition of the Principia. In 1701, Newton resigned the Lucasian chair, but not to retire. He decamped to London to become first warden and then master of the Royal Mint, transforming what should have been a comfortable sinecure into a crusade. During the Great Recoinage, he estimated that a fifth of British coins were counterfeit and forged an investigative operation that would not have shamed a modern prosecutor, cultivating informers, assembling evidence, and sending clippers to the gallows. Newton's administrative ferocity is an undervalued part of his scientific character. Precision in coinage, like precision in experiment, was a matter of national order. Privately, Newton poured thousands of pages into alchemy and biblical chronology and embraced a theology at odds with official Anglican doctrine. He admired Christ, but not the Trinity. He studied prophecy as seriously as he studied parabolas. That inner life never upended his public career, thanks partly to the royal dispensation that allowed his Lucasian tenure without ordination, and partly to his own secrecy. But it reminds us that the European new science was built by minds that saw no neat dividing line between the physical and the spiritual. Odd facts to keep. The most celebrated professor of his age often lectured to an empty room, and the same man who mathematized the heavens also hunted counterfeiters through London's alleys. The Lucasian Chair was his title. His workshop was the universe. Episode 3. William Whiston, 1702 to 1711, the comet's evangelist. Newton's chosen successor had a different temperament. William Whiston, tall, energetic, and pugnacious, took the Lucasian chair in 1702 and turned it toward the public. If Newton had been reclusive, Whiston was missionary. His 1696 bestseller, A New Theory of the Earth, welded scripture to Newtonian physics with an audacity that made even friends blink. The Earth began as a comet, he argued, and the Genesis flood was caused when our planet swept through the watery tail of another, drenching the world in 40 days of rain. In a culture hungry for reconciliation between revelation and the new mechanics, Whiston's cometary catastrophism was both controversial and, for a time, fashionable. John Locke and Newton read him attentively. Clergymen sparred with him in pamphlets and pulpits. Whiston did not keep the science in the classroom. He took natural philosophy to London coffeehouses, partnering with Francis Hawksby the Younger to perform experiments, optics, pneumatics, hydrostatics, while he explained the Newtonian worldview to paying audiences. These lecture demonstrations, at Buttons and elsewhere, were part of a new urban science culture in which spectacle and pedagogy overlapped, sparks leapt, air pumps thumped, and the calculus, never mentioned by name, moved in the background as a way of grasping change. Whiston's habit of digressing into theology sometimes ruffled patrons, but he helped create the template for public science in Britain. Then came longitude, the great practical problem of the age. With the mathematician Humphrey Ditton, Whiston proposed a system of moored signal ships to fire timed rockets upward. Navigators would triangulate position by the difference between the flash and the sound, and by compass bearing to known stations. He also advocated observing eclipses of Jupiter's moons as celestial clocks at sea, ingenious in theory, maddening on a rolling deck. These schemes, loudly promoted in 1713, helped push Parliament to pass the Longitude Act of 1714 and establish prizes for practical solutions. Whiston never won those prizes, but his agitation moved the state to treat navigational science as a matter of national policy. Whiston's downfall at Cambridge arrived via theology, not trigonometry. A convinced Arian, he publicly denied the doctrine of the Trinity and advocated a primitive Christianity he believed closer to the Apostolic Church. In 1710, he was deprived of the Lucasian Chair and expelled from the university. By 1711, his Cambridge career was effectively over. He made his living as a writer and lecturer and produced a translation of the complete works of Josephus, 1737, that became an English-language standard for generations, used by scholars and lay readers alike. Odd facts to keep. Whiston forecast public interest in eclipses by lecturing on the great 1715 event in Covent Garden. He printed a chart of comet paths with the mapmaker John Senex, and his longitude rockets, though never adopted, left a whiff of gunpowder in the annals of navigation. He was a Newtonian who turned popularizer and a professor whose convictions cost him his chair. Episode 4. Nicholas Saunderson, 1711 to 1739. The blind mathematician who taught Cambridge to see. After Whiston's stormy exit, the university elected Nicholas Saunderson, a Yorkshireman blinded by smallpox in infancy. In an era when impairment often meant exclusion, Saunderson's ascent to the Lucasian Chair made him a public symbol of intellect's independence from sight. He did not trade on sympathy. Students flocked because he was brilliant and because he made Newton's system, mechanics, optics, fluxions, feel like a working toolkit rather than a recondite theory. He was elected a Fellow of the Royal Society in 1718 and became one of the most influential teachers in early 18th century Cambridge. Saunderson's signature invention was his palpable arithmetic, a tactile calculating board, arrays of holes into which he placed pairs of pegs, large and small, to represent digits 0 to 9. By laying several squares in a row, he formed multi-digit numbers, aligned them above or below one another, and executed addition, subtraction, multiplication, division, and often left square roots to mental calculation. He also used peg and string boards to draft geometric figures by touch. The device was not a parlor trick but a working prosthesis for research and teaching, allowing him to perform long calculations in real time. It prefigured in spirit both the modern geoboard and accessible design in STEM. Although he published little during his life, Saunderson's lectures circulated in manuscript and guided a generation. After his death, his family, assisted by John Colson, the next Lucasian professor, edited and published his Elements of Algebra and the Method of Fluxions, applied to a select number of useful problems, the latter pairing calculus exercises with explanations of Newton's fluence and a broad introduction to natural philosophy. These books, used at Woolwich and beyond, show Saunderson's classroom genius, concrete problems, stepwise analysis, and explicit bridges between calculus and mechanics. That applications ethos was crucial to making fluxions more than a national badge in Britain's calculus versus differentials culture. His fame carried into philosophy. Denis Diderot cast a dying Saunderson as a character in Letter on the Blind, a meditation on perception and knowledge that uses the mathematician to argue that reason's reach is not bounded by the senses. Historians of statistics have even argued that Saunderson may have anticipated ideas later associated with Bayes' theorem, an intriguing, if contested, claim that underlines how much of his thinking circulated orally. He was also sociable, a competent flautist, a robust rider who local law says enjoyed hunting on horseback with a guide. The image is irresistible. Cambridge's blind professor, feeling the wind on his face, memorizing the countryside by hoofbeats. Saunderson died in 1739, likely of scurvy, and was buried at Boxworth near Cambridge. He had married Abigail Dickens in 1723. They had 2 children. His students remembered him as the professor who did not have the use of his eyes, but taught others to use theirs. In institutional history, his tenure marks the moment when the Lucasian Chair became not just a laurel of discovery, but a platform for pedagogy, where Newtonian ideas were digested into a curriculum and where accessible methods, literal in Saunderson's case, proved that mathematical insight could be taught, not merely revealed. Epilogue to Part 1. From Barrow's geometric bridge to Newton's universal mechanics. From Whiston's comets and coffeehouse showmanship to Saunderson's palpable arithmetic, the first 4 Lucasian professors turned a newly endowed chair into a European engine for ideas. The next episodes bring translators and reformers, John Colson, Edward Waring, a chemist cleric, Isaac Milner, calculator engineer, Charles Babbage, and then the long 19th and 20th centuries of Stokes, Larmor, Dirac, Lighthill, Hawking, Green, and Cates, each leaving a new instrument on the mantelpiece of science. Episode 5. John Colson, 1739 to 1760. The translator who opened Newton's black box. John Colson did not arrive at Cambridge with the aura of an original theorist. He came as a consummate expositor, steady, pious, and stubbornly practical, who believed that the right book in the right language could change what a nation knows. A Staffordshire clergyman's son, educated first at Lichfield Grammar and briefly at Christ Church, Oxford, where he left without taking a degree, Colson made his way by teaching Master of Sir Joseph Williamson's Mathematical School in Rochester, then Vicar of Chalk in Kent, and eventually a Cambridge lecturer at Sidney, Sussex. In 1713, the Royal Society made him a Fellow. Only in mid-life did he pivot decisively to Cambridge, winning the Lucasian Chair in 1739 and keeping his parish duties along the way, a reminder that 18th-century mathematics in Britain often wore a clerical collar. Colson's claim on history is not a single theorem, but a door he unlocked. In 1736, he produced the first English translation of Isaac Newton's long-shelved method of fluxions and infinite series, adding a running perpetual comment to guide readers through the work. Newton had drafted the treatise in Latin back in 1671, then declined to publish. Colson's version, learned, patient, and resolutely didactic, finally naturalized Newton's calculus for English readers outside specialist Latin circles. In effect, he turned a private manuscript into a textbook. The book's title page, crowded with promises about curved lines and applications, shows Colson's intent: take fluxions off the shrine and put them on the desk. In those pages, students encountered more than nomenclature. They found the working habits of Newtonian analysis, now speaking English. While the continental tradition was racing ahead with Euler and D'Alembert, Cambridge had tended to sheath calculus in geometric rhetoric. Colson's careful commentary helped the next generation connect Newton's dots and, ironically, prepared the ground for later reformers who would bring Leibnizian notation to the tripos. Translation can be a kind of revolution by stealth. Colson's scholarly temper shows in another gentler act of mediation. He helped Nicholas Saunderson's family bring the blind professor's teaching into print, editing and ushering into the world Saunderson's Elements of Algebra, 1740, and the posthumous method of fluxions applied to a select number of useful problems, with additions in the 1750s. If Colson's own classroom left few artifacts, his editorial shepherding ensured that Saunderson's tactile, example-driven pedagogy survived as living texts at Woolwich and beyond. Yet Colson was not only a curator of other men's ideas. In a short, quirky paper for the Philosophical Transactions, he proposed what he called negativo-affirmativo arithmetic, a signed digit scheme that replaces large digits with smaller ones carrying negative marks. It looks like a parlor trick until you realize you are reading an 18th century anticipation of balanced numeral representations, now used in efficient computer arithmetic. The idea resurfaced in later mathematical writing, Modern historians trace some of the first systematic exploration of negative base or signed digit systems to Colson's 1720s note. Odd fact, the fifth Lucasian professor thus dabbled in what we would now call number representation for fast computation. Another bridge he built ran to Italy. Maria Gaetana Agnesi's Istituzioni Analitiche, 1748, a masterclass in calculus pedagogy, found its English voice through Colson. His translation, prepared before his death and published posthumously in 1801 under the supervision of the astronomer clergyman John Hellins and with Francis Maceres's patronage, helped fix Agnesi's reputation in the English-speaking world. To read it beside his Newton translation is to see Colson's vocation. He wanted the newest mathematics to be teachable. Hath he trust? So the portrait of Colson is not of a showman or a system builder, but of a craftsman of clarity. He held a parish, kept a college lectern warm, and by translating, editing, and occasionally inventing, made the Lucasian Chair a conduit, not just a pedestal. If Isaac Barrow had passed Newton a torch, Colson widened the corridor so the light would travel. Episode 6. Edward Waring, 1760 to 1798, the analyst of Pleely. Edward Waring came up from Shropshire with a talent so plain that Cambridge bent its rules to accommodate him. A Magdalen College sizar, who rose to senior wrangler in 1757, he was elected Lucasian professor just 3 years later. Young, brilliant, and not yet even an M.A., the degree was granted by royal mandate so he could take the chair. From that perch, which he would occupy until his death, Waring attempted to drag British algebra into line with continental analysis. He succeeded unevenly, and left behind one of number theory's great stubborn questions. The bare facts of his life are deceptively quiet. He married Mary Oswell in 1776, practiced medicine for a time around Cambridge and St. Ives, battled severe myopia and a shy temperament, and eventually retired to Pleely near Shrewsbury, tending an estate and his notebooks. Waring was elected a Fellow of the Royal Society in 1763, and 2 decades later awarded its Copley Medal. He was not a podium charmer, and he did not found a school. Yet his books, Miscellanea Analytica, 1762, and Meditationes Algebraicae, 1770, with later editions, moved with a seriousness that impressed Lagrange. In tone, they can be prickly and opaque. In content, they are rich mines of results. The Waring question, framed in 1770, is famously simple to ask. For each exponent k, is there a finite number s so that every natural number is a sum of at most SSSKKth powers? He hazarded specific values, 4 squares, 9 cubes, 19 biquadrates, conjectures now recited to generations of students. The general problem was finally proved true by David Hilbert in 1909. Across the 20th century, Hardy, Littlewood, Vinogradov, and others fixed or bounded many of Waring's specific constants. It is a case study in how a Lucasian professor's musing can set a century of number theory to work. Waring's mathematical range exceeded that one conjecture. He revisited the algebraic theory of equations. He classified higher plane curves in a way that sharpened Newton's and Cramer's earlier schemes. He wrote on series and convergence, including a discussion of what we now call D'Alembert's ratio test. And he published a result about primes ascribed to his friend John Wilson. The identity, p minus 1 factorial, is congruent to negative 1 modulo p minus 1 factorial, that now bears Wilson's name, for which Lagrange later supplied a proof. Waring even included, alongside a restatement of every even number is the sum of 2 primes, the suggestion that every odd number is itself prime, or the sum of 3 primes, foreshadowing the weak Goldbach theme that subsequent centuries would refine and in our day settled for sufficiently large integers. For all that, Waring's reputation suffered in his own country. Reviewers harped on his style. Learned but thorny, ingenious but inelegant, a torrent of propositions without the pedagogical polish of an Euler. MacTutor's distilled verdict that he was one of the profoundest mathematicians of the century whose exposition hid his worth captures the paradox. The Lucasian Chair did not make him a celebrity. It gave him cover to write the books that would earn, slowly, the esteem of mathematicians who read past the gristle to the meat. The personal portrait complicates further. Waring belonged to the Hyson Club with William Paley. He took an MD in 1767. He tended patients at Addenbrooke's Hospital. He withdrew from the Royal Society in his 60s on account of age. He was provincial in residence but cosmopolitan in reading, tracking continental algebra when many in Cambridge clung to fluxional geometry. He probably never delivered a charismatic course. He may never have wanted to. He married late, settled into Shropshire's rhythms, and died in 1798, buried near the Severn countryside that had shaped his thrift and patience. From that quiet life came a problem set still open enough to occupy giants a century later. Odd facts to keep. Waring took the chair so young that an MA had to be issued by royal mandate. He practiced medicine despite severe short-sightedness, and he championed continental analysis at Cambridge before it was fashionable. On the page, he could be austere. In the algebra, he was bold. Episode 7, Isaac Milner, 1798 to 1820. The Evangelical Chemist of Queens. If Waring was the analyst of Cleely, Isaac Milner was the engineer of institutions, part chemist, part college president, part churchman, and part quietly relentless organizer. Born in Leeds in 1750, pulled from school at 10 on his father's death, and apprenticed to a weaver, Milner clambered back into education through his elder brother Joseph's patronage, entered Queen's as a sizar in 1770, and streaked through Cambridge as senior wrangler, 1774, and Smith's prizeman. The Royal Society elected him a Fellow in 1780. He served as the first Jacksonian Professor of Natural Philosophy, 1782 to 1792. The route is Dickensian in outline, scientific in content, poverty, patronage, and then prestige by sheer ability. Milner's science was of the pneumatic and electrical age. In a 1789 paper to the Royal Society, he described experiments on producing nitrous acid and nitrous air, terms of the phlogiston era, by electrical means, part of the chemistry of airs that preoccupied British laboratories in the decades straddling Priestley and Cavendish. The work sits precisely at the cusp where 18th-century affinity theories meet 19th-century stoichiometry. Sparks, vessels, measured diminutions of common air, and their conversion into acids. It was not a parlor curiosity. It was an attempt to make reactive nitrogen chemistry reproducible and useful Wikimedia Commons. He was also increasingly an architect of Cambridge life. As president of Queen's from 1788, Milner reshaped the college's tone and intake, and, along with the charismatic parish priest Charles Simeon, became a pillar of the evangelical revival within the university. Queen's as a nursery of evangelicals is a shorthand that simplifies a complicated career. The underlying fact is that Milner recruited for intellect and piety together and made the lodge itself a kind of laboratory full of apparatus and argument. He was named Dean of Carlisle in 1791, though he rarely resided there for long stretches, preferring to press reforms and experiment in Cambridge. 50 treasures. His best-known secular influence, though, comes with a friendship on the road. In 1784 to 85, Milner travelled on the continent with the young MP William Wilberforce. They read Philip Doddridge's The Rise and Progress of Religion in the Soul aloud. They argued. Wilberforce's mind and later his public life tilted. Historians disagree over timing and emphasis, but Milner's role in the great change that set Wilberforce on the abolitionist path is clear enough in the record and cherished in evangelical memory. It is an odd thread to find in a Lucasian story, except that Cambridge's mathematics and its morals have never been as separable as we pretend. Then, in 1798, Milner took the Lucasian Chair. By the late 18th century, the duties were as much ceremonial and examining as they were lecturing. A 19th-century biographical notice remarks that Milner delivered no lectures in the post. He certainly examined for the Smith's prizes. And nobody seems to have minded. By then, he was carrying Queen's, Carlisle, and a busy scientific and advisory life. The Lucasian professorship added a laurel. It did not define the man. What did he leave? In science, a set of careful papers and a reputation for experimental competence. In the church and university, a cadre of trained students and a reputation for administrative will. In public life, the catalytic push given to an abolitionist statesman. Those who knew him remembered his intellect, the materials cluttering his rooms, and his physical bulk, an imposing figure whose mind ran faster than his body. Milner died in 1820, closing a Lucasian chapter that was as much institutional as it was mathematical. Odd facts to keep. Milner began as a weaver's apprentice. Later, as a computer for the board of longitude, he checked the numbers that guided ships. And while Lucasian professor, he seems never to have delivered a formal course. All told, a craftsman of chemistry and conscience. Episode 8. Charles Babbage, 1828 to 1839. The engine builder who wanted a new kind of university. By the time Charles Babbage inherited the Lucasian Chair, Cambridge mathematics had begun to loosen its geometric grip. The 1812 Analytical Society that he founded with John Herschel and George Peacock had already pushed the university toward Leibnizian notation and continental analysis, translating Lacroix and smuggling the DDDs and partials into Senate House examinations. In 1828, with that student revolt now half won, Babbage took the chair and almost immediately set about arguing that Cambridge should be something more than a finishing school for exam takers. He was notoriously not a dutiful lecturer. George Biddell Airy, one of his Lucasian predecessors in that volatile 1820s sequence, thought Babbage's indifference to lecturing should be made an issue. William Whewell balked at Babbage's proposed reform program, and Babbage himself, always more comfortable in a workshop than a classroom, seems never to have delivered the promised course on political economy. Instead, he wrote, Reflections on the Decline of Science in England, 1830, took a blunderbuss to the Royal Society's culture. On the Economy of Machinery and Manufactures, 1832, anatomized industrial organization with an analyst's eye. The Lucasian Chair for Babbage was a platform from which to shout that science and industry needed new institutions. And of course there were engines. Babbage's difference engine, conceived to mechanize the production of accurate tables, drew state funds, a brilliant engineer, Joseph Clement, and then years of delay, friction and collapse as costs rose and tempers frayed. Out of that wreckage came a more audacious design. The analytical engine, a general-purpose, programmable machine with a store, memory, a mill, processor, conditional branches, and punched card control. He designed, he never completed one, but the architecture reads like a prophecy, and Ada Lovelace's 1843 notes on Menabrea's account made the machine intelligible to readers who would not live to see it realized. In the long hindsight of computing, the Lucasian Chair briefly sheltered the right imagination in the wrong century. Babbage's tenure with the university was spiky. His relation to the public could be spikier still. He tallied broken panes of glass. He kept a ledger of London street nuisances. He campaigned, sometimes comically, sometimes ferociously, against organ grinders. A man who dreamed of mechanical precision found himself tormented by urban chaos. It makes a strange counterpoint to his broader political vision. Broader franchise, a reformed scientific establishment, universities that valued research and practical arts alongside the classics. He twice stood for Parliament. He had, in other words, a reformer's impatience with almost everything. Odd fact. While he held the most famous mathematics chair in Britain, he never actually gave a Lucasian lecture, the Public Domain Review. The reckoning on Babbage at Cambridge is complicated. His difference engine failed in construction but succeeded in inspiring a new kind of thinking about labor, reliability, and error. His analytical engine was never built but is now understood as the first clear design for a universal computer. His books on science and manufacture were read by engineers who would equip the Victorian world, and his analytical society helped reshape the mathematics that fed the 19th century physical sciences. If the Lucasian chair had sometimes been a laurel to wear, for Babbage it was a switch to prod a university and a country toward the future. End of part 2. Next, the line runs through a turbulent 1820s interlude, Woodhouse, Turton, Airy, then steadies into the long Victorian tenure of Stokes, the electrodynamics and relativity of Larmor, the quantum revolution of Dirac, the applied sweep of Lighthill, the cosmological reach of Hawking, string theory with Green, and soft matter with Cates. The chair endures, the problems change. Episode 9, Robert Woodhouse, 1820 to 1822. The quiet reformer who changed Cambridge's notation. Robert Woodhouse's life looks modest from a distance. Norwich-born in 1773, educated at Gonville and Caius, senior wrangler and first Smith's prizeman in 1795, fellow of the Royal Society by 1802. Yet he is the hinge on which Cambridge mathematics began to swing from Newton's fluxions to continental analysis. Woodhouse is the reason later undergraduates, Herschel, Peacock, Babbage, could imagine writing d/dxd/dxd/dx and integral sign without sacrilege. The Lucasian chair he won in 1820 was honorable but not lucrative. After 2 years he resigned, famously because the stipend was too small, and accepted the better-paid Plumian professorship of astronomy and experimental philosophy. That post came with practical responsibilities, the brand-new Cambridge Observatory, transit instruments, and the keeping of accurate time. In effect, Woodhouse swapped the laurels of Lucas for the levers and clocks of the observatory, becoming its first director. The decision shaped the rest of his career and, through the observatory's routines, the habits of Cambridge science. His intellectual revolution had begun long before. In 1803, he published The Principles of Analytical Calculation, a dense, exacting book that insisted calculus should be done on a purely algebraic footing, prying it away from geometric limits and infinitesimals and toward the series-based Lagrangian methods, then transforming the continent. The argument was not style alone, it was substance. If analysis were recast in general symbols and series, its results would be clearer, more portable, and more fertile. Cambridge's older generation largely shrugged, the younger one took notes. Woodhouse followed with work on elliptic integrals, 1804, and textbooks, treatise on plane and spherical trigonometry, 1809, isoprometrical problems and the calculus of variations, 1810, and treatise on astronomy, 1812, that seeded the examination rooms with his new analysis. Herschel and Peacock later said openly that Woodhouse had started the shift they carried into the Tripos as the Analytical Society's campaign. There was a personal wager behind the public one. Fellows of Cambridge colleges could not marry. Woodhouse wanted a family. He also needed an income that would allow it. When he became Plumian professor, 1822, he resigned his fellowship and married Harriet, Norwich-born like himself, whose brother, the architect William Wilkins, would give Britain the stone face of the National Gallery and the classical lines of Downing College. The mathematical reformer, in other words, joined his fortunes to a family remaking British architecture. Odd fact. Woodhouse's marriage was literally made possible by the salary differential between Lucasian and Plumian posts. His later years were practical and administrative, the work of a scholar who loved instruments as much as ideas. He supervised the installation and adjustment of the observatory's transit telescopes and clocks and tried to knit theory to observation, an astronomer's version of the algebra geometry détente he had argued for in 1803. Ill health curtailed his activity. He died in 1827, 5 years after leaving the Lucasian chair. To students, he left treatises. To Cambridge, he left an observatory capable of better, more regular measurements. To British mathematics, he left a change of grammar that would, decades later, feel natural. Without Woodhouse, the Analytical Society's DDDs and H-partials would have sounded more foreign, and Cambridge's 19th century would have been poorer in symbol and in spirit. Astrophysics Data System. Episode 10, Thomas Turton, 1822 to 1826. the mathematician who became a bishop and wrote a hymn tune. If Woodhouse's Lucasian years point forward to analysis, Thomas Turton's point outward, to the curious and sometimes uneasy conversation between mathematics and the Church of England that marked so much of Cambridge life. Born at Hatfield in 1780, Turton arrived at Cambridge through Queen's and St. Catherine's, took senior wrangler in 1805 and was named Equal Smith's Prizeman. He was elected Fellow of St. Catherine's the next year, climbed the tutorial ladder, and in 1822 stepped into the Lucasian Chair. On paper, it is the pinnacle for a mathematician. In Turton's case, it was prelude. 4 years later, he left the Lucasian to become Regius Professor of Divinity, 1827 to 1842, then Dean of Peterborough, Dean of Westminster, and finally Bishop of Ely, 1845 to 1864. What did he do mathematically in those Lucasian years? Unlike Waring or Woodhouse, Turton did not push a new theory or rescript a curriculum. His significance is institutional and cultural, a senior wrangler occupying Isaac Newton's chair while his own vocation was pulling him steadily toward theology and church governance. He had a hand in the day-to-day academic life, examinations, appointments, the negotiation of a curriculum in which Euclid still loomed over everything. And then he moved on. Whether that looks like a detour or a design depends on how we read the 19th century university, which never neatly separated mathematical eminence from ecclesiastical preferment. As an author, Turton's strongest voice is theological and polemical. He wrote on the text of the English Bible and published a much-discussed pamphlet in 1834, Thoughts on the Admission of Persons Without Regard to Their Religious Opinions to Certain Degrees in the Universities of England, a contribution to the bruising debate over religious tests for degrees. He also produced works on Eucharistic doctrine from an Anglican vantage. These titles, alongside his long service as Regius Professor and then as Dean and Bishop, situate Turton among the Victorian church intellectuals who thought deeply about institutions, conscience, and law. One more thread: his role in the university press, the Pitt Press, where theological controversy and pedagogy met, and where Turton's prose was as much administrative instrument as it was scholarship. And then there is the Turton few expect to find on the Lucasian roll, the composer. Two of his hymn tunes, most notably Ely, found their way into Hymns Ancient and Modern, the great Victorian hymnal. The mental picture is irresistible: a Lucasian professor, future bishop, shaping congregational melody. Odd fact, of all Newton's successors, Turton may be the only one to have left a tune as well as a treatise. He died in 1864 and was buried at Kensal Green Cemetery, a metropolitan resting place for many of his era's public men, Westminster Abbey. From the standpoint of the chair's intellectual history, Turton's tenure reads like a pause between pushes. Woodhouse had argued for analysis. Airy and Babbage would press for a research university. Turton shepherded a great office with the caution of a churchman. At a minimum, his years remind us that the Lucasian professorship has never been a single, fixed thing. Sometimes it is a platform for discovery. Sometimes it is a sounding board for reform. Sometimes it is simply a high station in the life of a university whose concerns run from optics to orthodoxy to hymnody. Episode 11, George Biddell Airy, 1826 to 1828. From Lucasian lecturer to timekeeper of the world. George Biddell Airy was already a prodigy of the Cambridge system. Senior wrangler in 1823, Smith's prizeman, protégé of the reformer George Peacock, when he took the Lucasian chair at 25. He did not linger. Within 2 years, he moved to the Plumian chair of astronomy and experimental philosophy, and in 1835 became Astronomer Royal, a position he would hold for nearly half a century. If Woodhouse shifted Cambridge's symbols, Airy yoked British science to the clocks, meridians, and measurements that would organize the Victorian world. Airy's scientific signature appears in 3 quite different places. First, optics. The diffraction-limited image of a point through a circular aperture is the Airy disk, the bright core and rings every telescope and microscope must reckon with. Airy's early papers on caustics and intensity near a focus introduced the Airy functions, special functions that still sit in handbooks and code libraries because they solve the simplest second-order ordinary differential equation with a turning point. Students encounter them in asymptotics, quantum tunneling, and wave propagation. It is a neat irony that a man who would later bend institutions toward mechanical precision began by quantifying the unavoidable fuzz on perfect images. Second, mechanics of solids. The Airy stress function collapses the tangle of equilibrium equations in two-dimensional elasticity into a single biharmonic equation, a method still taught to engineers learning how plates bend and how cracks concentrate stress. As with the Airy disk, the idea's longevity is a measure of its simplicity. Choose a potential whose derivatives are the stresses, satisfy boundary conditions, solve a fourth-order PDE-PRS Kelly. Third, and most consequential for everyday life, time and place. Airy designed the Airy Transit Circle at Greenwich, the instrument that in 1851 defined the Royal Observatory's meridian. Internationally, by a vote in 1884, that meridian became the world's prime meridian. Under Airy, Greenwich's clock stars, transit timings, and ingenious distribution systems turned mean solar time at the observatory into Greenwich Mean Time, first to the railways and telegraphs, then to everyone's pocket watch. He inherited the famous 1 p.m. time ball, installed in 1833 by his predecessor John Pond, and mechanized its drop with an electric signal from the Shepherd master clock in the 1850s, while championing telegraphic time distribution across Britain. To stand on the brass line at Greenwich is, in a real sense, to stand on Airy's institutional idea, a single meridian, a single time. His career was not without controversy. The discovery of Neptune in 1846 has long been told as a nationalistic drama in which Airy, cautious or dilatory, depending on the teller, failed to secure the British claim for John Couch Adams, while the Frenchman Urbain Le Verrier's prediction led Johann Galle straight to the planet. The documentary record is complicated, and modern historians have softened the caricature of Airy as mere bureaucrat. What is clear is that he pushed Cambridge computation and Greenwich observation into a productive partnership, and that he was savvy enough to recognize the institutional power of regular, reliable data. Airy also loved a good experiment. His Harton-Colliery pendulum observations, 1854, measured the difference in gravity between the top and bottom of a 383-meter shaft, yielding an estimate for Earth's mean density, a Victorian feat of precision in damp, difficult conditions. Two more Airy eponyms round out the picture: Airy points, the optimal supports for a metrology bar to minimize end tilt, and the Airy hypothesis in geodesy, isostasy, adopted later by geophysicists to model how mountains float on a plastic substratum. In each case, the same imagination shows: find a simple governing quantity, treat the system as a whole, design around the inevitable error. The private Airy humanizes the public one. In 1830, he married Richarda Smith. Her first name is not a typo, and together they had 9 children, several of whom died young. One daughter, Hilda, married the mathematician Edward Ruth. A son, Hubert, became a physician known for studies of migraine, which his father also suffered. Airy's own recollections are full of Playford in Suffolk, of pea-shooters at school, and of the happy commotion of family at the observatory. Odd facts for a man of meridians and clocks, a wife named Richarda, and a household that mixed astronomy with amateur watercolors and music. Airy's Lucasian tenure was brief, but the chair's tradition of weaving mathematics into the nation's fabric, coins for Newton, longitudes for Whiston, runs directly through him. He made the sky a clock and the clock a standard. Few professors anywhere have changed so many daily lives. Encyclopedia Britannica, Episode 12, Joshua King, 1839 to 1849, the president who kept Cambridge's house. After Babbage's reforming thunder, the Lucasian professorship passed to Joshua King, a Queen's man with an enormous Cambridge reputation and a vanishingly small list of publications. Born in 1798 and educated at Hawkshead Grammar School, King came up to Queen's took senior wrangler in 1819, and entered university legend as a student of seemingly inexhaustible power. In 1832, he became president of Queen's College, a post he held until his death a quarter-century later. In 1839, he added Lucasian professor to his titles. The decade that followed belongs to the administrative and social life of the university as much as to its mathematics. What did King do as Lucasian? The honest answer is that he steadied the institution. He served on committees, presided over college business, and took a stint as vice-chancellor, 1833–34. He resigned the chair in 1849 owing to ill health and died in 1857. There is little technical work to point to, no theory with his name, no text that reformed a syllabus. But there is an unmistakable pattern of service, the duties that keep a collegiate university viable through periods of change. Seen in this light, King's Lucasian decade is the connective tissue between Babbage's activism and Stokes's long scientific reign. The college remembered him with affection and ceremony. In 1829, 3 years before he became president, former and present pupils subscribed 300 guineas for a full-length portrait by Sir William Beechey to hang in Queen's Old Hall, an extraordinary tribute to a tutor not yet 40. It is small, but telling evidence of his influence as a teacher and college man. After his death, he was first commemorated in the antechapel at Queen's. Later, his monument was moved to Mill Road Cemetery. Odd fact, of all the Lucasian professors, King may be the only one whose most visible relic in Cambridge is a portrait funded by his own students. What larger story does King's career tell? That the Lucasian Chair by the 1840s was embedded in a university whose energies were as much social and administrative as they were technical. The 1820s had seen symbolic battles over notation and pedagogy. The 1830s and 1840s were a time of consolidating reforms, regularizing examinations, and expanding the university's public reach. King's role as college president, hosting, mentoring, arbitrating, mattered to that process. If he published little, he influenced much through offices and rooms. Several contemporary and later notices emphasized that gap between expectation and print. Even so, the institutional record makes clear that he was, in every practical sense, one of the university's working leaders. James Clerk Maxwell Foundation. The personal portrait is, by design, almost private. King's fame rested on undergraduate brilliance, senior wrangler, the classic Cambridge laurel, and on a network of former pupils who remained loyal for life. It is easy, in writing a history of ideas, to undervalue such figures. But every scientific chair has its guardians as well as its innovators, and in the Lucasian story, King's decade gave Stokes a stable platform on which to build 50 years of mathematical physics. That is not a theorem, it is a kind of husbandry. Episode 13, George Gabriel Stokes, 1849 to 1903, A Half-Century of Motion, Light and Institutions. When George Gabriel Stokes rose from his desk in Lensfield Cottage to lecture, Cambridge listened not because he was theatrical, he wasn't, but because his mind made difficult things look inevitable. Born in Screen, County Sligo, to an Anglican clergyman, Stokes came to Pembroke College in 1837, left as senior wrangler and first Smith's prizeman in 1841, and by 1849 had stepped into the Lucasian chair he would hold for 54 years, the longest tenure in the chair's history. Cambridge wrapped itself around him, Fellow, Master of Pembroke in his final year, Secretary and then President of the Royal Society, and for a time even sent him to Parliament as one of the 2 members of Parliament for the university. It is hard to think of another scientist whose name touches so many corners of 19th century physics and its institutions. Stokes's name is a small atlas of modern science. In fluid mechanics, Stokes' law gives the viscous drag on a tiny sphere moving through a fluid. Fd equals 6 pi mu rv, Fd equals 6 pi mu rv, a result he obtained in the 1851 paper on the effect of the internal friction of fluids on the motion of pendulums. That one equation has explained everything from how fine dust settles to why clouds hang in the sky, and it remains the starting point for microrheology, aerosol physics, and blood sedimentation. The law is the low Reynolds number face of what we now call Stokes flow, the creeping flow limit of the Navier-Stokes equations. In wave motion, Stokes's nonlinear theory of surface waves led to the Stokes wave and the tiny yet consequential Stokes drift, the net Lagrangian push of water parcels under moving waves. Each result is a lesson in his style. Pare the phenomena to a clean limit, solve exactly, and carry the formula into practice. He ranged just as confidently in optics. In 1852, in the massive paper On the Change of Refrangibility of Light, he showed that materials such as fluorite and quinine absorb invisible ultraviolet and re-emit visible light. In a footnote, one of the most productive in physics, he coined the word fluorescence, and the systematic shift to longer wavelength that so often accompanies emission took his name as the Stokes shift. 2 years earlier, his Stokes parameters gave a convenient experiment-ready vector description of the polarization state of light, the backbone of modern polarimetry from telescopes to tissue imaging. The same taste for asymptotics that gave him simple physical formulas also led to the Stokes phenomenon. His analysis of how exponentially small terms in asymptotic series switch on or off across lines in the complex plane, a Victorian puzzle later smoothed by Berry and others. Taken together, these are not just results. They are modes of seeing. Even Stokes's theorem carries his institutional signature. In 1854, he set, without proof, a generalization of Green's theorem as a problem on the Smith's Prize examination. Maxwell himself sat the paper, and the result took on his name because he broadcast it, examined it, and turned it into mathematical currency. Historians have traced the seed to a 1850 letter from William Thomson, Lord Kelvin, but it was Stokes who made it public property. The theorem's journey from private correspondence to exam room says something about the way he worked. Rather than grand treatises, he preferred papers, lectures, letters, and problems that sharpened practice. The public Stokes was an organizer as much as an originator. He served as Secretary of the Royal Society for an unprecedented 31 years, 1854 to 1885. Then, as its President, 1885 to 1890, reading and refereeing manuscripts, corralling programs, and quietly deciding which projects and people should move forward. He was knighted with a baronetcy in 1889, elected MP for the Cambridge University constituency in 1887, and, in the last year of his life, became Master of Pembroke. One measure of his institutional reach is that Cambridge undergraduates founded the Stokes Society in 1909 as a science club in his honor. It is still active. Another is that the CGS unit of kinematic viscosity, the Stokes, keeps his name in every fluid mechanics lab book. Odd facts humanize the list. Stokes married Mary Susanna Robinson, daughter of the Armagh astronomer Thomas Romney Robinson, linking his Cambridge household to an Irish observatory. He was also a man of steady religious conviction who delivered Gifford lectures on natural theology in 1891 and 1893. And there is poignancy. 2 of his 5 children died in infancy. Another son, a physician, died at 30. The mixture, domestic joy, private grief, and public honor, is not unusual in Victorian lives, but it sits in sharper focus because Stokes's scientific voice is so impersonal. What ties the technical to the personal is a governing sensibility. In fluids, he asked what motion looks like when inertia vanishes. In optics, what light does when energy is shed. In mathematics, what expansions hide just below the threshold of approximation. He turned such edge cases into standards, and he built the committees, syllabuses, and journals that made those standards travel. When he died in 1903, the Lucasian Chair passed to his former student Joseph Larmor, and with it passed a Cambridge that Stokes himself had helped to craft, an ecosystem where analysis, experiment, and institution co-evolved. Few scientists change daily life. Stokes did, from the viscosity in a lab beaker to the polarized skylight over a ship at sea. His was a half-century of patient victories. Episode 14, Joseph Larmor, 1903 to 1932, Electrons, Ether, and the Precession of a Century. When Sir Joseph Larmor succeeded Stokes in 1903, he brought the Lucasian Chair into the electron age. Born in Magheragol, County Antrim, and educated in Belfast before coming Senior Wrangler 1880 and First Smith's Prizeman at St John's, Larmor began as a Cambridge lecturer, spent 5 years as professor in Galway, then returned to build a research school at the boundary of mathematical physics and emerging electrical science. He arrived at the chair not as a fluid mechanician or geometer, but as a theorist who had already attempted a unification of matter and ether. Between 1894 and 1897, Larmor published a trilogy on a dynamical theory of the electric and luminiferous medium, culminating in Part 3, 1897, where electrons appear as singularities in a continuous ether and where the equations of motion for charges foreshadow the relativistic transformations that would soon bear Lorenz's name. His book Ether and Matter, 1900, an Adams Prize essay, consolidated those ideas into a full-dress theory of matter as electrical in origin, with electrons as the atoms of electricity and the ether as the stage on which they move. The program would not survive Einstein's two relativity theories intact, but at the time it organized a great deal of British physics. Three notions keep Larmor's name vibrant across physics. First, the Larmor formula gives the power radiated by a non-relativistic accelerating charge, a bridge between the motion of electrons and the energy carried away as light. Second, Larmor precession describes how a magnetic moment processes about a magnetic field with angular frequency omega equals the absolute value of gamma b. It is the clockwork at the heart of NMR, EPR, magnetic resonance imaging, and much of solid-state physics. Third, Larmor's theorem and his anticipatory use of Lorentz transformations tied together moving frames, magnetism, and the apparent dynamics of electrons long before special relativity was canon. These were not footnotes to his ether. They were the usable parts of a theory that practitioners never abandoned. The Lucasian professorship gave Larmor a platform. The Royal Society multiplied his reach. Elected FRS in 1892, he served as one of its secretaries, 1901 to 12, later receiving the Royal Medal, 1915, and Copley Medal, 1921, for his scientific work. He delivered the Bakerian lecture in 1909. His influence traveled not just through papers, but through editorial labor, correspondence, and the patient care of institutions. He edited the posthumous works of Stokes, Kelvin, and Cavendish, placing Cambridge's 19th century canon within easy reach of 20th century readers. If Stokes linked science to governance via the Royal Society and a brief spell in Parliament, Larmor took the parliamentary route even more directly. He represented Cambridge University at Westminster from 1911 to 1922, a conservative voice who championed universities and technical education during a turbulent decade that included war, franchise reform, and the Irish question. He was knighted in 1909. Larmor's public roles mattered because they run exactly through his scientific temperament. He wanted physics to rest on firm mechanical foundations and universities to rest on secure civic ones. On the great question of the age, relativity, Larmor stood athwart the traffic. He had independently reached transformation laws equivalent to Lorenz's and even glimpsed time dilation for electrons. But he never accepted general relativity's curved spacetime, and he oscillated in his support for special relativity, trying repeatedly to retain an ether. In a celebrated 1920 plenary address, he publicly argued for the ether against Einstein's general theory, a sign not of stubbornness alone, but of the intellectual commitments of a generation trained to regard space as a physical medium. To modern eyes, this looks like resistance. To his contemporaries, it looked like a serious, if ultimately losing, attempt to reconcile the new kinematics with the older fabric of physics. The personal Larmor is quieter than the public one. He never married, was famously modest, and, as college law has it, once opposed the installation of baths in St. John's with the conservative quip that the college had done perfectly well without them for centuries. only to become a regular bather once they were installed. It is the kind of anecdote Cambridge remembers because it condenses a character, careful, conservative in habit, yet willing to embrace a change when it proved its worth. Odd fact, while he was the Lucasian professor, Larmor edited the two-volume memoir and scientific correspondence of the late Sir George Gabriel Stokes, 1907, a pupil erecting the archive of his master. History repaid the favour. Stokes's papers keep Larmor's name on their title pages. Larmor's electron theory keeps Stokes's institutional world alive in its prefaces and dedications. When Larmor retired in 1932, the chair passed to Paul Dirac, and the Lucasian line turned directly into quantum mechanics. But in the half-century between Stokes's appointment and Larmor's retirement, the chair had already carried Cambridge from viscous drag to radiating electrons, from polarized skylight to precessing spins. Episode 15. Paul Adrien Maurice Dirac, Lucasian professor 1932 to 1969. When Paul Dirac took the Lucasian chair in 1932, he did not so much inherit a throne as he quietly occupied a workshop where modern physics was being machined into shape. The son of a Swiss schoolmaster and an English librarian, educated first as an engineer and then as a mathematician, Dirac had arrived at Cambridge in the 1920s and already changed physics by the time the university handed him Isaac Newton's old title. His relativistic equation for the electron, 1928, welded quantum mechanics to special relativity with a startling grace. From it flowed the prediction of antiparticles, matter's mirror image, an idea vindicated when the positron was found in 1932. 2 years after becoming Lucasian professor, he shared the 1933 Nobel Prize in Physics with Erwin Schrödinger. Dirac's way with symbols helped define how generations would think quantum mechanics. In his 1930 textbook, The Principles of Quantum Mechanics, he popularized the delta function, a sharp theoretical spike used to idealize point-like events. Mathematicians would later rehabilitate it as a distribution, but in the hands of Dirac, it became indispensable to physics. A decade later, he introduced the compact, elegant bracket language, phi-psi, that made quantum states and operators feel as manipulable as algebra. If Heisenberg had given quantum mechanics its matrices, Dirac gave it its grammar. From the Lucasian chair, he also ranged into ideas that sounded like science fiction, but were built on clean mathematics. In 1931, he showed that if the universe contained even a single magnetic monopole, a lone north or south magnetic charge, then the electric charges of all particles had to be quantized in discrete units, as we observe. No monopole has ever been seen, but the argument remains one of the most beautiful what-ifs in theoretical physics. In the late 1930s, he chased numerical coincidences about the cosmos, the so-called large numbers hypothesis, suggesting that certain fundamental ratios might vary with cosmic time. The claims were audacious, sometimes controversial, but always rooted in an aesthetic faith that beautiful equations stand a better chance of being true. War work did not suit Dirac's temperament, but he contributed. During World War II, he worked on problems relevant to isotope separation and the theory behind gas centrifuges, and after the war he returned to Cambridge to pursue deep structural questions about physics. In a pair of now classic moves, he developed the Hamiltonian theory for systems with constraints and introduced the Dirac bracket, giving modern gauge theories a geometric backbone. His 1950 paper on generalized Hamiltonian dynamics and his 1964 Yeshiva lectures became standard references for quantizing constrained systems. As Lucasian professor, Dirac lectured sparingly, wrote tersely, and nurtured a small cohort through sheer clarity of thought. The chair did not make him a public figure. Cambridge already knew his strangeness and his brilliance. Students learned that when Dirac asked a question, there was a good chance it was the only question that mattered. His personal life was also spare, but, by those who knew him, unexpectedly warm. In 1937, he married Margit Mansi Wigner of Budapest, the sister of Nobel laureate Eugene Wigner. He adopted her 2 children, and the couple later had 2 daughters together. He was notably averse to honours. He declined a knighthood because he disliked the idea of being called Sir Paul, but he accepted the Order of Merit in 1973. Colleagues at Cambridge joked about a unit of conversational brevity, the Dirac, equal to 1 word per hour. Like many jokes, it stuck because it felt true. Odd fact, elegantly on brand. Dirac popularized a tabletop topological demonstration now called the Dirac belt trick, where a belt or plate must be rotated twice 720 degrees to return to its original configuration, a kinesthetic way to feel how spin-half objects behave. It is physics as sleight of hand, revealing the deep geometry underneath the everyday. Dirac retired from the Lucasian Chair in 1969 and decamped to Florida State University, where he surprised colleagues by being more sociable, walking to work, swimming in nearby lakes, co-authoring papers into his 80s. He died in Tallahassee in 1984, leaving a style as much as a set of results, a conviction that fidelity to mathematics, spare, exact, and beautiful, could lead the way. Episode 16, Sir Michael James Lighthill, Lucasian Professor 1969 to 1979. If Dirac gave physics a grammar, James Lighthill gave applied mathematics a voice, literally in the noise of jets and metaphorically in how applied analysis could speak to the modern world. Born in Paris to British parents, Lighthill arrived at Cambridge during the war years and quickly distinguished himself in supersonic aerodynamics. But it was in the 1950s, before he assumed the Lucasian Chair, that he wrote 2 papers that founded aeroacoustics, on sound generated aerodynamically, parts 1 and 2, which showed how turbulent flows radiate sound. From those analyses came Lighthill's famous 8th power law, the startling scaling that jet noise power rises roughly with the 8th power of flow speed. This was not an ivory tower curiosity. It guided engineers on everything from aircraft engine design to noise abatement. When he returned to Cambridge as Lucasian Professor in 1969, Lighthill brought with him a resume unlike any predecessors, Director of the Royal Aircraft Establishment at Farnborough by age 35, and then a Royal Society Research Professor at Imperial College. He was mathematical aerodynamicist, fluid mechanician, and public scientist all at once. In the lecture room, he preferred first principles and physical pictures, hence textbooks that became classics. The slim but powerful An Introduction to Fourier Analysis and Generalized Functions, 1958, and The Monumental Waves in Fluids, 1978. A tour through sound, shocks, water waves, and internal waves that trained generations of engineers and mathematicians to think about dispersive media with quantitative elegance. Lighthill's Cambridge was a place where mathematics and industry constantly conversed. His work on high-speed flows fed into real policy and real machines. His wave theory informed oceanography and meteorology. His tastes ran broad enough that many contemporaries called him a polymath. He loved to chair inaugural lectures outside his field and to offer dazzling codas linking the theme, Egyptology, literature, engineering, back to mathematics. He delighted in models that captured essence with minimal fuss. One of his charming legacies, often discussed by later authors, is the low Reynolds number squirmer model for microorganisms, part of a lineage of work that seeded today's active matter hydrodynamics. He could, in short, be fearlessly opinionated when a field's rhetoric outpaced its results. In 1972 to 73, he authored the UK Science Research Council Survey of Artificial Intelligence, now called the Lighthill Report. Written in crystal prose, it catalogued central difficulties, combinatorial explosion chief among them, and argued that grand claims in AI were premature. For better and worse, it helped trigger a sharp contraction in British AI funding, the original AI winter. The BBC even staged a televised debate pitting Lighthill against leading AI researchers. If you watch it now, you see a mathematician asking, quite insistently, for mechanisms and measures. Lighthill's personal style was courtly and exacting, his hobbies strenuous. He adored open-water swimming and became the first person to circumnavigate the Channel Island of Sark, a feat he repeated several times. In 1998, aged 74, he died of a heart attack during yet another attempt. It is difficult to imagine a more Lighthill end, in motion, in water, doing something that was part romantic challenge and part experiment. How far can a body, properly prepared, go? By the time he left the Lucasian Chair in 1979 to become Provost of University College London, applied mathematics had been indelibly woven into the chair's identity. Fluid dynamics and acoustics joined celestial mechanics and quantum theory as worthy heirs of Newton's seat. The field would be ready, in 1979, for a cosmologist with a voice synthesizer and an audacious idea about black holes. Episode 17, Stephen William Hawking, Lucasian Professor 1979 to 2009. Stephen Hawking's Lucasian tenure is a saga of improbable endurance and audacious theory. He came to Cambridge in 1962, was diagnosed with motor neuron disease, ALS, at 21, and, after an initial collapse, set about the most productive 40-year act in modern theoretical physics. In the late 1960s and early 1970s, he adapted Roger Penrose's global methods in general relativity to prove the inevitability of singularities, regions where classical space-time must break down, both in gravitational collapse and, working backwards in time, at the Big Bang. Those results rewired cosmology. The universe's beginning and a black hole's interior ceased to be speculative pathology and became precise theorems. Astrophysics data system. Then came the shock of 1974. Black holes are not entirely black. When quantum fields are allowed to dance on curved spacetime, horizons glow with a thermal spectrum. Small black holes evaporate. In a brief Nature paper with a modest title, Black Hole Explosions, Hawking introduced what the world now calls Hawking radiation. With it arrived a new thermodynamics of spacetime and a generational puzzle about information. If black holes evaporate, what happens to the quantum information that falls in? The paradox has driven decades of work across gravity and quantum theory. From the Lucasian Chair, Hawking combined this quantum gravitational imagination with a taste for the cosmological grand stage. In 1983, with James Hartle, he proposed the no-boundary wave function for the universe, a path integral over compact geometries that, in a sense, lets time turn into space at the beginning, removing a classical singular boundary. Whether or not the proposal is the last word on initial conditions, it reframed what a beginning could mean. These were not merely technical innovations, they were cultural events. In 1988, Hawking published A Brief History of Time, a brisk, often mischievous tour of cosmology for non-specialists. It sat on bestseller lists for years, sold tens of millions of copies, and made a wheelchair-using theoretical physicist a household name, an improbable outcome that quietly rearranged public expectations of who gets to explain the universe. Whether you finished the book or not became a running joke. The important thing was that you tried. His personal story fused with the science. Born on the 8th of January 1942, exactly 300 years after Galileo's death, Hawking outlived the prognoses of ALS by half a century, raising a family, writing bestsellers, and using a computerized voice to lecture across the world. The juxtaposition, frailty of body, ferocity of mind, made him into an emblem as much as a scientist. He held the Lucasian Chair until 2009, then moved to a research directorship at DAMTP, continuing to publish and to spar about information loss and cosmology until his death in 2018. Few academics have ever turned a professorship into such a platform for both ideas and inspiration. Odd facts. Perfectly Hawking. He loved practical jokes. He cameoed on The Simpsons and Star Trek, The Next Generation. And his synthetic voice, American accented by default, became so iconic that when newer voices became available, he refused to change it. But the most telling detail may be one of dates. Born on Galileo's death anniversary, he died on Einstein's birthday. He would have smiled at the symmetry, then rolled his eyes at the sentimentality. Episode 18, Michael Boris Green, Lucasian Professor, 2009 to 2015. By the time Michael Green took the Lucasian Chair in 2009, theoretical physics had acquired a new lingua franca, strings. Green had been one of its earliest and steeliest architects. With John Schwartz in the early 1980s, he rebuilt superstring theory from a struggling curiosity into a consistent framework by showing how a seemingly fatal sickness, quantum anomalies, could cancel in a 10-dimensional theory with the right ingredients. The Green-Schwartz mechanism, unfurled in 1984, ignited the first superstring revolution, persuading a critical mass of physicists that strings could unify quantum mechanics and gravity without the ultraviolet catastrophes that plague point particle theories. As Lucasian professor, Green did not treat string theory as a monolith, but as a workshop. Anomalies, dualities, branes, the gauge-gravity correspondence, pieces that talk to quantum field theory and to pure mathematics. For the generation that followed, much of their apprenticeship came through the two-volume textbook Superstring Theory, 1987, which Green co-authored with Schwartz and Edward Whiston. Those volumes, still in use today, did for the subject what Dirac's principles did for quantum mechanics. They gave it a clear, rigorous idiom and made it teachable. Green's Lucasian years coincided with a broader cultural shift. The Large Hadron Collider turned on. Dark energy and precision cosmology flourished, and the strings versus everything else debates grew loud in the press. Green himself remained imperturbable, using the chair to build bridges across Cambridge's high-energy theory groups and to keep the conversation anchored in calculation. In 2014, he shared the Fundamental Physics Prize for opening new perspectives on quantum gravity and the unification of forces. After stepping down from the Lucasian Chair in 2015, he continued research as an emeritus at Cambridge and, more recently, moved to Queen Mary University of London, staying active in a field that has diversified far beyond the 1980s blueprint he helped draw. Odds and ends. Green once quipped that the number 496, the dimension of the special gauge groups that make anomaly cancellation work, popped out of the algebra like a cosmic wink. String theorists still tell the story of the stormy night the calculation finally balanced, and if you spot well-thumbed copies of Green-Schwartz-Witten in student offices, note the lineage. Lucasian pages that, in a neat historical loop, trace back to Dirac's taste for economical formalism. Episode 19, Michael Elmhurst Cates, Lucasian Professor, 2015 to the present. Under Mike Cates, the Lucasian Chair looks again a little different, closer to kitchens, factories, oceans, and living cells. Cates is a theorist of soft matter, the messy middle ground between crystals and ideal gases, where polymers tangle, colloids crowd, emulsions jam, and bacteria swim. His signature achievement is to build statistical mechanical theories that extract universal structure from complexity, precise constitutive laws for gooey materials, minimal field theories for suspensions, and most visibly the modern theoretical framework for active matter, where particles consume energy to propel themselves and thus live forever out of equilibrium. One storyline has come to symbolize this shift: motility-induced phase separation, MIPS. With collaborator Julian Tailleur and others, Cates showed how even purely repulsive self-propelled particles can spontaneously demix into dense and dilute phases, because particles slow down when they hit crowds, which in turn draws more particles in, a positive feedback that mimics liquid-gas separation without attractions. The resulting continuum and field theories, active models B, B plus H, and cousins, map the non-equilibrium physics of swimmers onto modified versions of equilibrium phase separation, while keeping the new terms, the entropy production, the odd stresses, that break time reversal symmetry at the heart of the story. It is a rare thing, an elegant bridge between the mathematics of pattern formation and the reality of living and synthetic microswimmers. The Lucasian Chair under Cates has also been institution building. Returning to Cambridge in 2015 after 2 decades at Edinburgh, where he held the venerable Chair of Natural Philosophy, He reorganized soft matter theory across DAMTP and the Cavendish, connecting polymer physicists to biophysicists to fluid dynamicists. His group's reach runs from granular avalanches to shear thickening suspensions, from the rheology of soft glasses to the hydrodynamics of swarming cells. If Hawking's chair broadcast the universe to the public, Cates's chair has broadcast that the physics of toothpaste, ketchup, and cytoplasm is a frontier rich in first principles. Cates's style, like Lighthill's in an earlier age, favors parsimonious models that can be falsified in the lab. He has given named lectures with titles like Active Matter and the Arrow of Life, foregrounding a question that threads through his work. When and how do non-equilibrium systems remember that they are far from equilibrium? The answer, he argues, sits in coarse-grained signatures, violations of detailed balance, measurable entropy production, odd elastic responses that survive to macro scales. The approach has earned him major prizes in rheology and statistical physics and the attention of engineers who design materials that thicken on impact or self-organize under flow. And an odd fact with a Lucasian echo, Cates trained with Sir Sam Edwards, the polymath who revolutionized polymer physics by treating tangled chains statistically, just as Dirac had treated quantum states. The through line is the Lucasian trick itself. Write down the right variables, be honest about approximations. Let mathematics illuminate the mundane. Appointed the 19th Lucasian professor on the 1st of July 2015, Cates continues to expand the chair's brief, from celestial to cellular, from strings to suspensions, without losing the Newtonian insistence that good equations should see what the eye cannot. Coda, from Dirac's austere equations to Lighthill's roaring jets, from Hawking's evaporating horizons to Green's vibrating strings, and onto Cates's churning colloids, the Lucasian chair has been less a throne than a set of tools passed hand to hand. The odd facts, Dirac's 1 word per hour Dirac, Lighthill's swims around Sark, Hawking's birthday symmetry with Galileo, are not footnotes so much as reminders. Science is a human story threaded through a lineage. The chair persists because each holder finds a new way to make mathematics answer the world. Part 6, Epilogue 1663 to 2025. What a 362-year relay tells us about science, teaching, and the strange lives of equations. 1. The chair as a workbench, not a throne. From the first Isaac to the latest Mike, the Lucasian chair keeps rewarding people who treat a title as permission to tinker. Barrow used it to carve a geometric path toward the calculus. Newton turned it into a legal shield for private revolutions. Whiston dragged it into coffeehouses full of pumps and sparks. Saunderson rebuilt arithmetic by touch. Colson retooled Newton's Latin for English classrooms. Waring set a conjectural beacon that number theory chased for centuries. Milner soldered apparatus and souls. Woodhouse swapped laurels for transit instruments. Airy nailed Britain's time to a line in Greenwich. Babbage proposed to mechanize thought itself. King kept the college house so the next era could work. Stokes, the patient sovereign of Victorian physics, stitched practice to principle. Larmor modeled matter as electricity and left us formulas that power MRI suites. Dirac pared quantum mechanics down to its grammar. Lighthill made turbulence speak in decibels. Hawking made horizons glow. Green cured anomalies. Cates formalized the self-driven swarms and jams of the soft world. Read straight through, the chair looks less like a crown and more like a particularly well-equipped bench, one that moves, era by era, to the corner of the lab or library where the world is most confusing. 2. The long fight over how to write, from fluxions to dx, dx, dx. A second theme is stylistic and therefore strategic. 18th century Cambridge clung to Newton's fluxions and geometric rhetoric. On the continent, Euler and Lagrange were turning calculus into a supple algebra. Colson's 1736 translation of Newton's method of fluxions gave Britain a shared text, but it didn't change the idiom. Woodhouse's Principles of Analytical Calculation, 1803, did. By insisting that analysis be carried on a purely algebraic footing, he taught a generation to think in symbols, and the Analytical Society, Herschel Peacock Babbage, smuggled the DDDs and hints into the Senate House. What looks like a quarrel over notation was, of course, a choice about research futures. By the time Stokes and Larmor hold the chair, the continuum between applied analysis and mathematical physics is firm enough that Lucasian equally means boundary layers, asymptotics, electrodynamics, and, eventually, quantum theory. Odd footnote of style, Colson's negativo-affirmativo arithmetic, a signed digit scheme to speed pen and paper calculation, reads like a fossil of modern number representation, an 18th century whisper of balanced ternary and carry-free arithmetic. 3. Instruments, institutions, and the making of standards. The Lucasian story refuses to separate ideas from devices or offices, mint and money. Newton's forensic mint work during the Great Recoinage, assayers, informers, and gallows made precision a statecraft. Longitude and rockets, Whiston's signal ship scheme and pamphlet wars pushed Parliament toward the Longitude Act, proof that flamboyant proposals can still sharpen a national question. Palpable arithmetic, Saunderson's pegboard deserves to be in the ancestry of today's accessible STEM design. Observatories and time, Woodhouse, then Airy, tie Cambridge and Greenwich to precision timing. Airy's transit circle and meridian turn local practice into world standard. Engines and organizations, Babbage's difference and analytical engines fail in metal but succeed on paper. His books on manufacture and on the decline of science prefigure research universities as we know them. Societies and exams, Stokes's half-century of Royal Society labour and his habit of slipping epical results, Stokes' theorem, into examination problems show how standards are domesticated. Policy documents. Lighthill's report on AI is a reminder that a Lucasian professor can chill or channel an entire field's funding with a single, elegantly argued memo. In each case, the instrument is also an institution. A coin die, a clock, an engine, a curriculum, a report, objects that outlive their makers and quietly discipline the work of others. 4. The chair and the church. The Lucasian line runs through pulpits and doctrinal storms. Newton's royal dispensation exempted the professor from ordination, letting heterodox conscience coexist with office. Whiston's Arianism cost him his livelihood. Milner helped build an evangelical cadre at Queen's. Turton left the chair to become a bishop and wrote a hymn tune, Ely, still sung. The moral may be simple. British science of this period grows inside, not outside, an ecclesiastical world, and the chair's protections and perils are shaped by that fact. 5. Disability and access. Saunderson and Hawking bookend a different kind of theme, invention in the face of constraint. Saunderson's tactile boards and string and peg geometry were not accommodations, but methods that shaped his teaching. He hunted on horseback by sound and stride count, and his lectures traveled in other people's hands. Hawking's motor neuron disease turned voice synthesizers and wheelchairs into lecture apparatus. The timbre of his American-accented voice became itself a scientific brand. Between them lies a principle. When a community invests in access, it recoups insight. 6. A cast of equations, and what they keep doing. Barrow's geometric FTC tucked the inverse relation between tangents and areas into rigor before symbols had a clear home. Newton's laws and fluxions fastened planetary dance to terrestrial fall. Waring's problem asked how many kth powers sufficed to build any whole number. It seeded a century of analytic number theory. Airy disk, airy stress, airy functions, bound optics, elasticity, and asymptotics into tractable kits. Stokes' law and Stokes' drift give creeping flows and surface waves their cleanest edges. Stokes' theorem turns flux and circulation into a higher dimensional handshake. Larmor formula and precession tie accelerating charges to light and magnetic moments to clocks. Dirac's equation marries spinors to relativity. Delta functions and bracket grammar make quantum calculation hospitable. Lighthill's acoustic analogy turns turbulence into sound fields and policy. Hawking radiation makes horizons thermodynamic. The no-boundary wave function reimagines beginnings. Green-Schwarz anomaly cancellation keeps gauge symmetry honest in a quantum world. motility-induced phase separation. Kate's shows how non-equilibrium drives its own kinds of order. Each equation is a character. Each continues to earn its keep. 7. The public, the popular, the odd. A Lucasian professor is periodically thrust into the piazza. Whiston did it on purpose, renting rooms and selling tickets to science. Babbage grumbled about organ grinders while proposing to reorder industry. Stokes served as an MP. Larmor spoke for Cambridge at Westminster. Lighthill argued AI into hibernation on national television. Hawking wrote a bestseller that haunted coffee tables. Green's 496 became a talisman of a new unification. Kate talks ketchup, toothpaste, and swimming bacteria to remind us that most matter in our hands is neither crystal nor gas. The odd facts: Barrow versus pirates, Airy's wife, Richarda, King's student-funded portrait, Dirac's belt trick, Lighthill circling Sark, Hawking refusing to change his voice, keep the lineage human. 8. What the baton passes felt like. Some handoffs were explicit and dramatic. Barrow resigning for Newton, Stokes paving a parliamentary royal path that Larmor would also walk. Others are historical rhymes. Woodhouse's algebraic program prepared the soil for Babbage's analytical society. Stokes's asymptotic sensibility echoes in Dirac's distributions and Lighthill's matched expansions. Hawking's paradox culture pose a clean impossibility and work toward resolution, reappears in Green's treatment of anomalies and in Cates's insistence that non-equilibrium materials can be given equilibrium-like field theories, plus the new symmetry-breaking terms they demand. In every era, the Lucasian Chair seems to find the mathematician who can write the usable story for the physics of the moment. 9. The timeline at a glance with one-line tags. Isaac Barrow, 1663 to 1669, geometric calculus, pirate-fighting classicist, mentor to Newton. Isaac Newton, 1669 to 1702, fluxions, color, universal gravitation, empty lecture rooms, very full universe, mint manhunter. William Whiston, 1702 to 1711, cometary Earth, coffeehouse science, longitude rockets, theology ends tenure. Nicholas Saunderson, 1711 to 1739, blind mathematician with tactile arithmetic, Newtonian pedagogue. John Colson, 1739 to 1760, translator teacher, Newton's fluxions into English, proto-signed digit arithmetic. Edward Waring, 1760 to 1798, analyst of Pleely, Waring's problem, doctor with severe myopia. Isaac Milner, 1798 to 1820, evangelical chemist administrator, Queen's president, Wilberforce's companion. Robert Woodhouse, 1820 to 1822, algebraises calculus, leaves Lucasian for Plumian and the observatory and marriage. Thomas Turton, 1822 to 1826, senior wrangler turned bishop, author of the hymn tune Ely. George Biddell Airy, 1826 to 1828, Airy disk and stress, Greenwich time and meridian, controversy and clocks. Charles Babbage, 1828 to 1839, engines on paper, reformer of university and manufacture, foe of organ grinders. Joshua King, 1839 to 1849, college president, institutional ballast between activism and a coming half-century of Stokes. George Gabriel Stokes, 1849 to 1903, viscosity, waves, polarization, asymptotics. Secretary-President of the Royal Society, Baronet. Joseph Larmor, 1903 to 1932, electrons and ether, radiative power, precession, Cambridge MP, knighthood. Paul Dirac, 1932 to 1969, relativistic quantum, positrons, delta-delta-delta functions, brackets, the quietist radical. M.J. Lighthill, 1969 to 1979, aeroacoustics, waves in fluids, AI winter, swam round Sark. Stephen Hawking, 1979 to 2009, singularities, Hawking radiation, no boundary, bestseller and cultural icon. Michael Green, 2009 to 2015, string anomalies cancelled, textbook architect, 496 and the first string revolution. Michael Cates, 2015, to present soft matter and active phase separation, non-equilibrium field theories for everyday stuff. 10. The future the chair is already pointing to. Each Lucasian pivot predicts a frontier. Cates's soft matter and active matter programs point to living physics, programmable materials, and climate-scale geophysical flows with microstructural rules. The mathematical styles now maturing in Cambridge, stochastic thermodynamics, data-driven closures for turbulence, topological phases in soft and quantum systems, look, in retrospect, like natural descendants of Stokes's asymptotics, Dirac's economy, Lighthill's modeling, and Green's structural cures for inconsistency. The chair's old question persists: what is the most compact, honest description of a complicated reality that we can use tomorrow? It is Newton's question reframed for every century. Closing scene. Imagine the anteroom of Trinity or Dam TP as a kind of time-compressed workshop. Barrow's Euclid open beside Newton's prism. Whiston's rocket diagram smudging Saunderson's pegboard. Colson's patient marginalia lining up with Woodhouse's algebraic laments. Airy's transit circle blueprint propped against Babbage's gear trains. Stokes's wave sketches clipped to Larmor's electron notes. Dirac's spinor algebra chalked right beside Lighthill's acoustic analogy. Hawking's path integrals curling past Green's world sheets, and Cates's active model B+. The odd facts, pirates, hymn tunes, organ grinders, belt tricks, time balls, swims around Sark, lie like dropped tools. And the work goes on. That is the secret of the Lucasian chair. There is always a next piece of ordinary reality waiting for the right equation, and always a human life, peculiar, stubborn, miraculous, willing to pick it up.